Hello and welcome to the Prelab video for the enthalpy of vaporization of water experiment, part of the General Chemistry 2 laboratory sequence at York College of Pennsylvania. Today I'm going to walk you through some of the theory that underlies the enthalpy of vaporization experiment, briefly show you the setup, and go through the pre-lab questions. We're going to make a separate video that will describe the calculations that you'll complete as part of this experiment, which are a little bit involved, and I hope you'll be willing to try them in an Excel spreadsheet to save you some time ultimately. So look for that video to show up as well. So the goal of our work in this experiment will be to determine the enthalpy of vaporization of water, and then to use that value to estimate the boiling point of water, which we already know to be 100 degrees Celsius, so we have a pretty good idea of what our answer should be when we're all said and done. Enthalpy of vaporization, enthalpy, remember, is a term referring to energy of a process happening at constant pressure, essentially. So we're looking at the energy to vaporize water, turn it from liquid into its gaseous form. That energy is usually quite large when it comes to vaporization, as opposed to the enthalpy of fusion, which would be melting a substance from its solid to its liquid phase, because when we vaporize, we're literally freeing the molecules from one another, overcoming the intermolecular force of attraction that holds them in the condensed liquid phase. So this is usually a pretty significant energetic term. So the vapor pressure, all liquids are vaporizing to a small extent at almost all temperatures, and that generates some pressure if you were to trap that in a closed container. We've talked about this in chapter 11 in our textbook, so I'll refer to those figures and to that section of chapter 11 that can help you. But you could make a graph of vapor pressure of any liquid versus temperature, and it would essentially have this exponential shape to it. This is exponential form. One of the points of interest would be the vapor pressure of that material at 1 atmosphere. So if I cross 1 atmosphere, what temperature does it require to force a liquid, if it was trapped in a container, to generate 1 atmosphere of pressure? Is what I'm considering here. This temperature would be what we call the normal boiling point of the liquid. And for water, we know that to be 100 degrees Celsius. So in other words, at 100 degrees Celsius, water, the liquid, pushes out with 1 atmosphere of pressure. Now in an unclosed pot, we know that the normal atmosphere would be pushing back with the same amount of pressure, and when those two pressures are equal, the liquid is said to be boiling, and every molecule in the liquid phase has an equal opportunity to convert to the gas phase. So how does this relate to enthalpy of vaporization? Well, if we take the natural logarithm of each of our pressure data points and the reciprocal of each of their temperatures, we get a shift in this graph, or a change, into this linear form. Now all straight lines are of the form y equals mx plus b. And our y, in this particular case, is the logarithm of our pressure values. And our x is the 1 over t values. So there's something special about the slope then. And it was Clausius and Clapeyron who first quantified this relationship. So this is now called the ClausiusClapeyron equation, that the slope is equal to the negative of the enthalpy of vaporization divided by R, the universal gas constant. But because we're dealing with energies, we're looking at the version of R that's 8.314 joules per mole Kelvin, not its ideal gas law form 0.08206. So here we're using the energy form of it. So today in lab, what we'll want to do is collect the vapor pressure of water at a variety of temperatures to make this graph. And when we make this graph, we'll be interested in the slope because we can simply solve for the slope, from the slope for the enthalpy of vaporization. So your data will be quite simple. You'll have two columns of data when you leave the lab today: pressure and temperature. It's the data analysis that will get to be quite tricky. As I said, look for a separate video that describes some of that, but in short, you'll take the pressures, convert them into logarithm values. Temperatures you'll convert to Kelvin, and then take the reciprocals and make this graph. Once you make the graph, you'll add the trend line and take the slope and set it equal to this combination. So your enthalpy of vaporization will simply be the negative of your slope times R. It's as easy as that. We can ignore the other piece of this graph's equation. It's just a constant. It's going to be unique to the specific material that we were working with. It's not part of our calculations at all. So how will we accomplish this goal? It's quite simple. I'll wheel in the setup that we're using today. Okay. All we need is some water and a means of measuring the pressure. Well, we're going to achieve that indirectly by measuring the volume of a sample of air trapped underwater. So I have a large beaker filled with water, essentially all the way to the top, a little bit of room so that I don't splash out, and a graduated cylinder. Graduated cylinder is going to allow me to measure the volume inside. I've filled my graduated cylinder up about 80 to 90% of the total height of the cylinder, not the markings on it, but rather almost the total height. I'm just going to turn it upside down, and once my finger's under the water, I can take it out, and then I can place this into the setup. Now that's all we need, and we'll just heat this up and cool it down as it goes. I've taken this liberty to make a clay triangle that I've bent a little bit just to rest it on top of that cylinder. I've learned from past years that this is not the most stable arrangement you could see, and so just that little bit of weight on the top of it is going to keep it from falling over. Now as we heat this up and cool it down, that bubble of air that's trapped inside the cylinder, whose volume I can now read, although it's upside down, be careful when you read that, whose volume I can read, will expand and contract with the temperature. Right now, the gas inside that bubble is mostly air, because I just started with the cylinder filled most of the way with water, so it would have been air on top of it. As we heat this up, we will be saturating that vapor space, that head space, with more and more water. We're going to be adding water vapor, which is going to expand the volume, but the pressure will remain constant inside that. So that's going to be the important key. So actually, when you leave the lab today, you won't have pressure versus temperature, you'll have volume versus temperature, and we're going to do the data conversions to turn the volume into pressures, which we'll use in our data analysis. So the setup is pretty easy. Please be careful not to get burned. There are no chemical hazards in today's work. You'll still be required to wear your safety glasses, but you might want to have the hot hands available, maybe even 2 sets of them. If you have to handle this beaker, you're going to bring it up to about 90 degrees Celsius today, 80 or 90 degrees Celsius. Certainly too hot for you to be grabbing it with your bare hands. Right? So make sure that you take the appropriate precautions for handling any hot glassware or water. Okay. Now let me go through the pre-lab questions that are part of this experiment. And a couple of these play a significant role in the calculations that you'll do as part of this lab. So let's pay good attention and make good notes of these in your laboratory notebook. Now the first one is actually just a refresher. We'd like to know what amount of acetone can be vaporized by 100 kilojoules of energy. So when we're vaporizing a substance, this occurs at constant temperature. And so the heat involved in such a process is not governed by the MC delta T equation that we've used frequently, but rather by the N delta H equation. So I can manipulate this to solve for the moles of acetone that will be vaporized. N will be Q divided by delta H. So we have 100 kilojoules of energy being added, and it requires 32 kilojoules to vaporize a mole of acetone. So that is 3.125 moles of acetone. So this can be converted to mass. By multiplying moles by the molar mass of acetone provided in the question as 58.08. So that is 182 grams of acetone could be vaporized by the addition of 100 kilojoules of energy. Our second question references the two-point Clausius-Clapeyron equation. This is the general form of the Clausius-Clapeyron equation, but for any two pressure-temperature combinations, P1, T1, and P2, T2, we could express ln of P2 over P1 equals negative delta H vaporization over R, 1 over T2 minus 1 over T1. Of course, it goes without saying, really, we have to have our temperatures in Kelvin when we do this. Our pressures could be in either, atmospheres or torr. As long as they are the same unit, it doesn't really matter what pressure they're in. So we're asked to use this equation to predict the delta H of carbon tetrachloride. And we have two pressure temperature combinations. So this is really just an algebra exercise. So the delta H of vaporization would be, I'm going to multiply the negative R times the ln of P2 over P1. Okay. So far that would equal positive delta H vaporization 1 over T2 minus 1 over T1. I'll just divide that over. So this whole thing then should be so I simply need to substitute negative 8.314 joules per mole Kelvin times the logarithm of P2. So you could choose to define whichever one you want as P1, P2. Generally we choose the higher temperature. So P2 would be the 836 over the 213 for P1. And in my denominator then, the 80 degrees Celsius would be T2. Converted to Kelvin, that's going to be 353.15 minus the 40 degrees Celsius converted to Kelvin, 313.15. And this comes out to be 31,400 joules per mole, or 31.4 kilojoules per mole. These are usually on the scale of thousands and 10,000s, so we're in the habit of converting them to kilojoules per mole. So this is the enthalpy of vaporization of carbon tetrachloride. Now you'll use this calculation in lab this week, and one of the top time saver techniques that I'll show you in the other video I'll be making is to program this equation into an Excel spreadsheet. Because look at how complicated and how many numbers you had to enter to get this answer. It would be much easier if you could have a spreadsheet simply reference each of these numbers 8, 9, 10 times, as opposed to you typing them into your calculator again and again and again to get 10 different delta H values for each of your data points that you collect today. Okay. All right, let's look at the third pre-lab question, which again uses the 2-point Clausius-Clapeyron expression. But this time we want to estimate the boiling point of carbon tetrachloride. So we're going to solve for a different part of the Clausius-Clapeyron equation. So again, this is a lot about algebra. If we define our P1, T1 as the 80 degrees Celsius point and the that would be 836 torr. My T2 is what I'm looking for, and P2 would be 760, normal atmospheric pressure. So I'll be looking to solve for T2. So again, there's some algebra that needs to be done first. I can get rid of both R and delta H. So I'm negative R divided by delta H times the ln of P2 over P1. That's equal to 1 over T2 minus 1 over T1. So I can add 1 over T1. Added to this, now because of the negative sign, I can just have it as minus R times the ln of P2 over P1, all divided by the delta H vaporization. Okay. That's 1 over T2. T2 would simply be the reciprocal. I'm not even going to bother to try to manipulate this. I'm just going to raise it all to the -1. Again, since I'll be doing a calculation just like this in the lab, I want to figure out how I can type this into an Excel cell so that it is done over and over again for me so that I can predict the boiling point of water. This is how you'll be predicting the boiling point of water when the time comes to do that calculation. For now, though, I simply need to substitute in 1 over my T1 is the 353.15 Kelvin minus 8.314 times the ln of P2, 760 over 836, divided by my enthalpy of vaporization. Now I calculated it in the last example, 31,400, and I am using the joules because this R is in joules per mole Kelvin, which I did not write. So that way my joules per mole cancel out. Okay? I'm going to have kelvins left as my unit ultimately. All that's going to get raised to the -1. I got intermediate there, 0.00286. 1 over kelvins raised to the -1, which would be 350 Kelvin. You could backtrack to Celsius if you'd like as well. So that'll be the pre-lab question. Again, you'll be using this calculation, this specific formula here, to calculate the boiling point of water in your lab this week. And then you'll average those boiling points and compare it to the known value of 100 degrees Celsius or 373 Kelvin. Okay. Again, Not too challenging in terms of the experimental work. You simply need a graduated cylinder, a large beaker, and a hot plate. Be careful of the temperature of the beaker. It won't look hot, but it will be plenty hot when you're working with it. We'll need a thermometer throughout the experiment to determine the temperature of the water. And from then on, it's a simple matter of the data analysis. And I'll show you that in a separate video. So good luck in the experiment, and I hope you have a nice time.